So backpropagation is an algorithm which is a chain rule of calculus, and as I have said, it is used to update the weights. So there is a tutorial here which explains this backpropagation. So what it does is in the forward pass, it computes the gradients and with respect to the loss function or cost function. So what is loss function is it is a metric which we use which we use to quantify the performance of the CNN, and we try to improve the performance based on this loss function. So the loss or cost function means the higher the loss, the worse the performance. So as we proceed through the training, we try to reduce this loss, and in that way we get a trained model which performs very good for the test set. And the way to do is we use optimizers to update the weights. So there are various optimization algorithms which uses the gradients and updates the weights. So the widely used are the stochastic gradient descent, and the others are Adam optimizers. So there are lot of optimizers which each have its own advantages and which we can use to update the weights. So this is how the basic CNN framework works. So there are the links are provided here. You can have a look at them if you are new to this. So that is not very important for the current talk. So I'll just proceed. So there is nothing missed here. So the only thing is the details. You can have a look at these links. The overall idea remains the same. Okay, so now coming to a residual convolution network. So this is an improvement over the conventional CNN. So why to do this is because the CNNs have a problem. The problem lies in the fact that if we increase the number of layers, so if we increase the depth of the CNN, we will logically expect to have a better performance, but that is not the case. So we suffer from a problem what is called as the vanishing gradient problem, and it basically lies in the fact that we use gradients to update the weights, and the problem is uh, if there are more layers, when we do the back propagation, the gradient values become very small, and there is hardly any training that hardly any training happens. So there is no performance improvement which we see, which we will ideally expect by increasing the number of layers. So to solve this problem, there was a solution provided which is called residual networks. So this is the crux of it. So we have a shortcut connection which we called which is the basic block of this ResNet, and our aim is to learn the residual. So f of x is the residual, and f of x plus x is the function which we want to learn. So the idea is what residual information which we need to add to the original image to get the features. So it basically becomes learning the residual function. So how this solves is we come to it next. As I have mentioned, we now formulate the layers as learning the residual function f of x instead of learning the the entire function h of x. Okay, so now it solves two problems. The first one being the main problem, which is the vanishing gradient. How it solves is, so this block is one of the layers, and we have this these blocks one after another as we go. So I'll come to that. So the thing is, the gradients can now directly flow from this path. So the higher layers which were facing the vanishing gradient problem, that is the gradients were becoming very small. So this shortcut path solves that problem. And add to that, it also solves an additional. It also has an additional advantage, being so I mentioned it here. So at some point, if it is optimal to learn the identity mapping, then it will be easier to push this f of x to 0, and we have the identity mapping. So this is the advantage which we do not have if we don't have this skip connection. So let's say we don't have this, then we'll have to learn the identity function by tuning this weights. So this is an additional burden, which is not present in the case of Residual Networks. So now, so this is the residual network. So the block which I have mentioned is stacked one after another, and we can have various architectures of ResNet. So we have ResNet 18, ResNet 32, 52, and so on. And the very basic is the ResNet 18, and which will use it for our task. So these are the set of convolution, so residual blocks, we can say. And then we have the usual fully connected classifier, FC classifier, which classifies it into one of the classes. And this is the residual block. It's basically convolutions followed by Bayes norm, and this is the activation function. So these are the intrinsics of CNNs. So if you have gone through the links, you will understand this. So this is the blocks which you have repeated one after another to build the architecture, ResNet 18 architecture. You can also have a look at the links here to learn more. And this is from the paper. So we have different, so using different configurations of convolution layers, we can have different architectures. So this block, a set of convolution layers, is repeated twice. This also repeated twice, and so on. So these things is just to represent that we have different architectures for ResNet. Okay, so having learned the ResNet, and which will use for the experiment, we now proceed to the steps of feature extraction. So yeah, so data augmentation. So so why we need data augmentation is because to train these networks we need huge amount of data, and sometimes we don't have that much, so we artificially generate data, and to increase the data size. So in this case, we have, this is the original image, and we do contrast enhancements, or do add noise, and flip it, rotate it, crop it. So using this, each image is converted into multiple copies, and this way we increase the size of the data, which helps in the training. And this we will see uh, practically in our demo session, the effect of with and without data augmentation. Okay, so this is the experiment. We will use the ResNet 18 as the base model, and to classify we need a fully connected layer, which is the last layer, and this we need to modify depending on the number of classes which we have. So in our case, we have 100 classes. So the length of this fully connected layer is 100. So basically there are 100 neurons in this layer, and we do initialization with Xavier, is a technique to initialize, and the learning rate of the fully connected layer and the rest of the network is set this way. So why this is because the learning rate of the fully connected layer is set higher, and the learning rate of the overall CNN part is kept lower. So before that, what is the learning rate? So the learning rate is uh, so it's like we need to update the weights. So how fast we update the weights is controlled by the learning rate parameter. If the learning rate is higher, so weights are updated. So weights are updated faster. The training of these layers happen faster. So the learning rate controls that learning, and then the models are trained for 10 epochs. So here in this case, we will, so what is the epoch? Epoch is the iteration. So we go through the entire data set for training, then we repeat this process again and again. So each process is called as epoch, and we can have multiple epochs, and the more the number of epochs, the better is the training. And we use the SGD optimizer, which is stochastic gradient descent, and the momentum of 0.9, and the learning rates are decayed by 0.1 factor. So why this is? Because as we proceed with the epochs, our network is learning. Then we don't want more changes, frequent updates in the weights, because it has already learned to some extent, and now we want to fine tune the weights and do not want major changes in the weights. So that is why we decay the learning rate by 0.1 factor. This is a factor. Then we get a train model, which we use to evaluate it on the test set. So next, move to demo session, and so it will take around 15 minutes, and then we will conclude with the references. So moving to the demo session. Is the screen visible?
Yes.
Okay. So this is what we had left. We are into collab.research.google.com, and this is the file which we used for scattering experiment. Now we will open a new file. Open notebook, and going to Google Drive. It automatically locates all the IP/YMB files in your drive. So these were provided in the workshop_content folder that will be provided to you, and you can access these files here. So Google Colab and CNN.Colab. Okay. So we proceed as it is. We do shift enter to run. We can see that it is connecting and allocating a GPU. It will show it here once it is done. It is connected, and then you can see around 15 GB of GPU has been allocated. Then we do the same process like last time to link this session, Google Colab session, to our drive, where you uploaded the workshop_content folder. We copy this code, paste it here, then enter. These are Linux commands. CD means change directory. We are going into the workshop_content folder, and ls means we are listing all the files there. So we should be able to see the dataset folder, without which we cannot proceed. So we have to ensure that this is the case. Then the visual pipeline is to do the imports. Once done. So as I said, we'll first look the performance without doing augmentation. So I access this train and test sets. So yeah, talking more about this is a PyTorch framework which we are using, and PyTorch is a deep learning framework, and there are several others like TensorFlow and Caffe. But for this session, we will be using PyTorch framework.
So Sagar, you may just want to spend just a minute or so explaining what deep learning means. Yeah, because many participants may know, but still, it's worth spending a minute or so on that. Yeah.
Yeah. So this is just a deep learning library which we use. So the concepts of deep learning is basically is centered around majorly centered around CNNs when we look into the images context. And so we have seen how we train it and what are the different components. And PyTorch is one of the framework which allows us to implement it easily. So this is a deep learning library. And so the benefit of using Colab is you do not need to install it on your machine. It already gets allocated to you, and all the things are already installed. So you can just start. So there are tutorials here which you can have a look. This is for images. It works for tabular data or audio and any data. The image, video, audio, even the text. There are different advanced topics such as reinforcement, which are beyond the scope here. So yeah, so this is the background of PyTorch, and so what we do here is yeah, so this is important concept I need to explain. So we provide the data in the form of batches. So there is each batch contains specific number of images, and we pass this image to the CNN and update the weights. That is how these algorithms work. So to do that, we have what is called a data loader, which does exactly that, and we specify here the batch size. In this case, it is 256. So uh, yeah, so it is 256, and so there are each time 256 images will pass, and there are some various other parameters like shuffle. So it will do some shuffling, which helps in the training, and this is a parameter which is the number of workers. So this is used for parallel processing, and this is not a very important parameter here to discuss. Yeah, so the main part is the batch size, and so this is how we get it. And the dataset size I'm printing here. So there are 600 images for train and for 607 images for train and 400 for test. So for the initial setup, we will use these images for training, and we will evaluate it on the test set. Without we won't be using augmentation, and we will see the effect of augmentation soon after this. So this will be clear why we need the augmentation. So we have 607 images which will be used for training, and this cell is just to display one of the images, so you can run it. And this is the class. So what we are doing basically, this is just the same thing which I explained. We use the ResNet 18 as the base model, and we add a classifier, linear classifier, which is this syntax is used to define a fully connected classifier. So you can see here is this is what it does. X into the weights, x into A transpose plus B is the weights, and x is the inputs. So this is what the PyTorch library provides us, and yeah, and we do the Xavier initialization of all these neurons, and the number of output neurons is 100. Yeah, so this is it. Then we define a method, or we can say function, to train the model. Here we define the various parameters such as which optimizer we will use, the scheduler, meaning how the learning rate should decay, and the number of epochs, and the criterion is the loss function. So the way we define the loss function affects our learning, and for various tasks we need to choose an appropriate loss function. So in this case, we are doing a classification experiment. So we need to use a entropy loss function, cross entropy loss. So this function defines all the procedure. So I'll quickly glance you through the code. If you can just run it, you can directly run. So yeah, so you have to set the model into the training mode while we do the training, and then we pass the inputs, meaning which are basically the images and the labels to the model here. So during the training step, we evaluate the criterion. We use the criterion loss function to evaluate the loss, and this is the main focus that we want to reduce this loss. So the training happens around this loss function. Then we, as I've explained, if it is the training phase, we do the back propagation. We back propagate this loss, and optimizer.step optimizes the weights. So as I've said, optimizer is used to update the weights. So this call to the optimizer will update the weights based on the loss and the gradients which were calculated by this step. So then these are the statistics. So we track it for each epoch. We track the loss function and the accuracy, and so that we can define where we need to stop, when we need to stop, and when we are satisfied with the accuracy. So this is it, and so it prints the loss function and the accuracy as and when the epoch proceeds, and we save the model. So just do shift enter or control enter. Then about this cell, so till now we have defined our functions or classes. So now we eventually use it here. We define the optimizer, we define the criterion, we define the model, and we define the scheduler, and we pass it to the train underscore model function, which we have just discussed with all these parameters which are defined here. So we train it for 10 epochs. We can run it for even more epochs. So for timing, we will run it for 5 epochs. So right now, the first epoch is running. So the first epoch takes a bit of a time because it loads the data and makes the data loaders. So it takes time. So everything is, if you followed the steps, you should be able to see this output here. So I'll quickly mention about what we expect. So we will see that our model is getting trained, and we get a very good train accuracy. But we will see that the test accuracy is not quite good. So this is because there is a problem called overfitting here. Since the data is less, we tend to overfit to the data. So this is the universal problem in the context of deep learning, particularly in the CNNs. So we need to have huge data. So that is why we use techniques such as data augmentation to synthetically create the data, and so that we can train. So let me wait a few seconds here. Okay. So till then it runs, I'll explain the next cell. So now we proceed to augmentation. So this cell you have to just run to augment the data. So it will access each and every file from the train folder, and it will create a train augmented folder and store all the augmented files there. So for that we use this library, which is Augmentus library. So so I would like to mention that this is the advantage of using these frameworks and Python. So we have all the libraries already written, so we can just use it. So what we do is we do the scale, translations, rotation, contrast enhancements, addition of Gaussian blur, do the cropping, flipping, then multiplying the channels, and so on. So yeah, you have to run this. So I've already run it, and I have the augmented folder here. I just open it. So this is what we obtain after augmentation. There are different kinds of transformations. So this will take a couple of minutes, say let's say 5 minutes. So since I already have it done, and I already have the augmented data, I'll just proceed. Before that, let's see what has happened here. Okay, so we can see that at the end of fourth epoch, our test accuracy is just 3%, but the train accuracy is 91%. So this is clearly the case of overfitting, and we don't want this. So we want comparable accuracy, train and test accuracy. So that is why we do the augmentation, and having done that, these numbers are the folder names. So I have already done it, so I'm not doing it now. Now we are repeating the same thing with the augmented folder, and this is same as before. Now we are calling this train model with the augmented data, and these are kept the same. So we are almost at the end of this demo. So we will see that we get a comparable train and test accuracy, and yeah, so this is just the repetition. Okay, so there are some other metrics which I have explained below, which I'll quickly cover them. So let's see what is the output here. So we will be having a model will be stored here. So the best model, best model and the final models will be stored here. So we'll use that to evaluate the test set. Yeah, to see the usage of GPU and whether to verify whether you are actually using the GPU or not, we can go to this tab section and click it. We can see that the active session, the current file, and the GPU used here. Out of 15 GB, we have used 9.8 GB. And if you to increase to use meaning if we increase the batch size, we will use the last part of GPU, and even the training will be faster. So that is up to us. Okay, so these are so now we evaluate it. We have what we call confusion metrics, and we can call this classification report. So it gives precision recall for each and every class. And yeah, the support means the number of images in the test set. So there are 4 images per class, and there are total of 100 classes. We get the precision recall and F1 scores for all the classes, and we take the average of it then. And this is what we have, the numbers. This is the accuracy, and this is the precision recall, and so on. So we see that we get a pretty good accuracy. And yeah, I think that's all. So these are some more functions I've written. You can go through them.
So good. I think, does that bring you to the end of your demonstration, Sagar?
Yeah, almost to the end. So
Okay,
I'll quickly
fine.
show. I'll wait for a few seconds and show
Yeah,
this.
yeah, fine.
Yeah, so till then I can go through the references. So these are the
Yes,
references.
yes.
Yeah, so this is our paper in which we have explained our deep scattering wavelet network feature extraction technique. And this is the original papers by papers of scattering wavelet network. So this Dr. Mallet initially proposed this. So to know more about the scattering wavelet network and the concepts, you can have a look at these references. And one more important paper is this. So this is for the residual networks. This is the CVPR paper, and so you can. This is a very nice paper. You must have a look at this. And there are papers of using deep learning for ear recognition. And these two papers summarizes the challenges, meaning submissions. So it summarizes all the approaches which were submitted by the participants. And yeah, that's all. Yeah. So we are also almost done here. So we can see that we have comparable train and test accuracy. So that's what we have achieved. And we have, so with this, we have seen two approaches for feature extraction, ear feature extraction, one which is based on deep learning, and the other which is based on multi-resolution feature extraction. And both of them have a similar performance. Yeah, so before conclude, I'll add one point. So although these accuracies are same for both the techniques, we will see the advantage of deep learning when we go for unconstrained ears. So for if the images are unconstrained, meaning if there are too many variations or it is not captured in a controlled environment, we see that the handcrafted based features have a slightly reduced performance. And so that is how we can, that is where we can use deep learning to
That is where deep
have,
learning has an advantage, isn't it?
yeah,
So that's
advantage.
where deep
So
learning.
we can use both
Good.
of them together
Right,
also to have
I
a
think we can.
better advantage.
Good, good.
So
I think we can
I think,
conclude the presentation here,
yeah, I think
right?
I
So it
conclude
was
here. Yeah.
very good. Okay. Good. We can conclude here.
We are left with last minute, sir.
Yeah.
Stop the recording.
So Gadre sir can
Shall I
say a
stop?
few.
Yeah.